Good day, everyone. Today I'm presenting our work, Personalization of Programming Education, and NLP-based bidimensional classification of programming exercises. This is a joint work with my colleagues Gijs Walravens, Mazyar Seraj, Lina Ochoa Venegas, and Mark van den Brand at Eindhoven University of Technology. So let me start by setting up the problem we're addressing. So programming education is experiencing a massive global growth. It's now recognized as a core literacy, similar to mathematics or science, but this creates a significant challenge. We're seeing mass classes with hundreds of students per course, and the problem is that the teaching methods we know best, personalized learning and active learning, are becoming incredibly time-consuming at this scale. So when you have hundreds of students, you simply can't provide individual feedback and tailored exercises the way you could with smaller groups. So this is driving the need for automated exercise systems that can maintain educational quality while reducing the workload. But these systems, they require a systematic understanding of existing exercises. Namely, what kind of exercises do these systems need to be working with? So what does the current landscape of exercise classification look like? First, there's a fundamental scaling problem, as mentioned before. Manual labeling of exercises becomes increasingly impractical as the volume of content and learners grow. Looking at existing approaches, they tend to focus on single dimensions. So for topic classification, most work relies on curricula and textbooks, but the main problem is these aren't data-driven. So they assume predefined frameworks rather than discovering topics from the exercises themselves. Then for difficulty classification, we see three main limitations. Some approaches use extensive performance metrics, but these require a large data set. These large data sets that aren't available for new exercises. And others rely on expert judgment, as this shows systematic bias. And mathematical approaches tend to produce overly broad categories that don't distinguish well between similar exercises. So what's needed is a systematic, automated approach that handles both dimensions, so topic and difficulty. And that's the gap we are addressing. So how do we address these classifications? We looked at domain-specific lexicons, which have shown remarkable success in other fields. But the problem is programming education lacks this dedicated lexicon. At the same time, there's been recent work using large language models like GPT-4 for exercise generation. While promising, these approaches face significant barriers. They have high computational costs, and more importantly, they lack interpretability. So these black box models make it difficult to understand or trust how exercises are being classified or generated, which is a real problem for educational quality assurance. Our approach positions itself as a resource-efficient and transparent alternative using lexicon-based NLP methods. Then this leads us to our two research questions. First, to what extent can machine learning and NLP methods effectively identify and classify educational topics in programming exercises? And secondly, to what extent can ML and NLP methods effectively predict difficulty levels of exercises? So these questions, they guide our investigation into whether automated classification can assist educators in understanding and organizing their exercise content at a scale. Our approach combines three components. So we start with exercise descriptions and a Python-specific lexicon. These feed into NLP methods that perform two tasks, so topic classification and difficulty prediction. And this bidimensional analysis then provides a comprehensive understanding for each exercise. And the idea is straightforward. If we can systematically understand what characterizes existing exercises, so both their topic and their difficulty, we can then use that understanding to support the creation of new and appropriate exercises for all kinds of different learning contexts. On to our methods. Our dataset consists of 106 Python programming exercises from 3 introductory programming courses at the TU Eindhoven. So each exercise is formatted as a Jupyter notebook with a description and a reference solution For difficulty prediction, we have student performance data from a subset of exercises, specifically 32 exercises across 5 different sets, which in the end gives us a total of 5,522 data points. For topic classification validation, we manually labeled exercises using established CS1 topics. 2 raters independently performed this labeling and then met to reach consensus on all exercises. This provides ground truth for evaluating our automatic topic modeling approach. We then construct the Python specific lexicon, which is a core component of our approach. So we built this lexicon systematically from 4 sources. So the first one is Python reserved words like return and lambda from the keyword module. Then built-in functions like print and range from the built-ins module. Third, data types like Boolean and integer from the official Python documentation. And lastly, general programming terms like variable and element from a Python educational textbook. So to maximize our filtering capability, we expanded the lexicon to include all variations of each word. So to be precise, with this we mean all the inflections of their lemmas. So for example, instead of only including integer, we also include integers. And for example, for the word set, we include it as a verb, a noun, and an adjective. So this expansion means we can match more instances when filtering the descriptions without losing semantic information. Then for topic classification, we use BERTopic, which recent research shows outperforms traditional methods like LDA and top2vec. The pipeline works as follows. First, we filter exercise descriptions using our lexicon to focus on programming relevant terms. Then we generate BERT embeddings, and these capture contextual relationships between the words. And here a key choice in our method is that we keep the stop words during the embedding to preserve the context, but then remove them before the next step to avoid noise in the topic representations. So next, we reduce dimensionality, and then we apply clustering to automatically determine the exercise groups. And finally, we identify representative words for each topic. Then we evaluate this in an ablation study across 100 iterations, comparing our full approach against variance without lexicon filtering, and also an approach without stop words during the embedding. Then to assess this, we use 5 different metrics. The ARI score for alignment with our manual topic labels, the NPMI and CV for the coherence of the topics, and lastly, the topic count and the outliers for the stability of the resulting topics. And for difficulty prediction, we use a supervised learning approach. We process exercise descriptions using TF-IDF factorization combined with our lexicon. So our difficulty metric is the average student score per exercise. This is an established approach in the literature, but we acknowledge the ongoing discussion surrounding the reliability of the difficulty level metric. Then we evaluate 5 supervised machine learning models, linear regression, ridge regression for regularization, lasso for feature selection, random forest to capture non-linear relationships, and SVM for handling complex patterns in high-dimensional space. Similar to topic modeling, we run 100 iterations, comparing our lexicon-based approach against the baseline without lexicon filtering. And we evaluate using the root mean squared error and the R-squared to assess both precision and reliability. Then onto the results. So what did the lexicon construction produce? So we ended up with 318 unique terms, which expanded to 715 variations. Then more importantly, we can look at the impact it had on the feature space. So for TF-IDF factorization, we went from around 2,000 features down to 246 features, which is an 88% reduction. And then for BERT embeddings, we reduced from a bit less than 2K to 715 features, which is still a reduction of 62%. Then, what did this lexicon achieve in combination with the BERTopic at topic modeling? So let's start with the classification accuracy, which is measured by the adjusted RAND index. So again, in the middle, we have our approach, and on the left, we have the baseline without our lexicon filtering, and on the right, the baseline that doesn't use stopwords in the embedding phase, but uses the lexicon. So here we see a clear improvement. The lexicon-based approaches achieve an ARI of 0.33 compared to the baseline's 0.21, which is a statistically significant difference. And furthermore, we see that the lexicon methods also show tighter boxes, so they reduce the variability across the 100 iterations, which means a more consistent performance. Then, moving to topic coherence, the results are a bit more mixed. So looking at the NPMI scores, we see that the approach without stopwords performs best, achieving a positive score of around 0.02, and the lexicon approach with stopwords and the baseline both score below 0. This indicates a worse than chance performance. And also notice that the baseline has a much wider box on the NPMI score, indicating even more inconsistent coherence. Then for the CV coherence metric, it tells a similar story, although a bit better performance. So again, removing the stopwords gives the best coherence score at about 0.6, and the baseline and lexicon with stopwords show intermediate performance around 0.45 or 0.48. So overall, all methods struggle with coherence, but the no stopwords variant performs best, and it does so consistently better than the baseline. Then for clustering stability, we look at the topic count consistency on the left, the lexicon approach with stopwords, so our suggested method, the middle one, produces the most stable number of topics with a tight distribution around 8 topics. The baseline varies wildly, anywhere from 2 to 11 topics across different runs. And so this stability is important because it means that the lexicon approach reliably identifies a consistent structure in the data. And lastly, on the right, outlier count shows how well the exercises fit into topics. So both lexicon approaches produce substantially fewer outliers, so around 8 to 10 exercises on average, compared to the baseline's 20 outliers. So fewer outliers means better defined topics, where most exercises are belonging to a specific cluster. Then moving to difficulty prediction results, we see a much more varied performance across our models. So at the top, linear and rich regression with lexicon filtering perform the best, achieving an R squared of around 0.37 and 0.41. With a root mean squared error of 0.05. So for these models, the lexicon method significantly improved the performance across iterations. Then for random forest, it showed poor performance with an R squared of about 0.24. And the lexicon still provides improvements here, but a more modest one. Then lastly, the lasso regression and SVM perform at the below chance level, so R squared less than 0. And notably here, also the lexicon provided no benefit in their performance. However, we also need to acknowledge some significant limitations. All models show a high variability across the 100 iterations. And even more critically, our best root mean squared error of 0.05 spans nearly the entire interquartile range of student scores. So this indicates that while the lexicon consistently improves performance, the practical utility remains a bit limited. So then what do these findings mean for educators? First, the Python-specific lexicon itself is a contribution. So it provides a shared vocabulary for representing fundamental programming topics. So this can support the design and evaluation of educational materials, and help standardize topic coverage across programming courses. Though we acknowledge it needs some further development and validation. Second, looking at our classification results, the lexicon combined with NLP methods effectively support topic-based exercise classification. This works well. However, the difficulty prediction is a whole different story. It still requires better metrics and more robust methods. Third and final, and maybe most important for practical applications, is our framework, which provides transparent and interpretable classifications, so educators can understand and trust how topics are identified. Comparing this to LLM-based approaches like GPT-4, which are black boxes with high computational costs. And from a research perspective, there are several directions forward. First, again, the lexicon itself, it needs a bit more work. So we need a mixed method approach to evaluate and extend it, both quantitatively and qualitatively. Then second, the framework expansion. So our bidimensional approach is just a starting point. Future work could explore additional dimensions like Bloom's taxonomy, cognitive complexity, and for example, learning outcome alignment. And critically, difficulty measurements remain an open research topic. So our results contribute to the ongoing discussion about how to use performance data to estimate the exercise difficulty. And third, this work is also an invitation to keep exploring the resource efficient solutions rather than defaulting to computationally expensive LLMs. And then finally, this classification framework serves as a building block for adaptive learning systems and intelligent tutoring. So systems that can tailor content to individual learners based on systematic understanding of the exercise characteristics. So let me wrap up by directly answering our two research questions. So first, can machine learning and NLP methods effectively identify and classify educational topics? Yes, our lexicon-based approaches significantly outperform the baseline with clear improvements in accuracy and stability. And this provides a transparent alternative to resource-intensive LLM approaches. And second, can these methods predict difficulty levels effectively? Here we see limited success. So the lexicon consistently improves performance across most models, but practical utility remains really constrained. So better difficulty metrics and expanded data sets are needed. Then our main contribution, first, a Python-specific lexicon for programming exercise classification. And second, a bidimensional framework for automated exercise generation systems. That wraps it up. Thank you for your attention.
So I'm understanding is that we have authors online, so we can ask questions and they will be able to answer.
Hello, everyone.
Yeah. Any questions?
Yeah, my question is regarding a possible application in the area of teaching large classes. When you are looking at classification of answers, students answering questions, something similar comes up where you may want to classify answers according to their relevance to the topic, according to their quality, but also you may want to classify answers with respect to you might want to group answers into baskets so that you can grade the answers and comment and give feedback in a more effective way in very large classes. So would your approach be applicable to that scenario?
Thanks for your question. Are you hearing me?
Yes, we can hear you. Yeah.
That's a very interesting question. So I think that the method that we developed could be, let's say, migrated and applied for the answers part. In particularly when you were like formulating the question, I thought that you could even see what constructs the students already know by looking at what they are using in the solution they are providing, right? And based on that, you could even suggest new exercises that they can fill in later. So if you see that a student is using like a more advanced construct, then you can suggest that later. But now, regarding your question about like grading the answers and providing more like tailored feedback, I think we could also use that in that regard, right? Like, so one thing is suggesting exercises, but then in the same way you can say, okay, you're using this construct, maybe you could think about, like improving the implementation by applying the following steps, sort of scaffolding them, like the development and the performance of the student.
Right. Any more questions? If not, then let's thank the speakers again.
Thank you.